pause the video and try this example. Try to draw what is the product suggested by this electron pushing arrow. Well, so far I've just redrawn the starting materials. Now we can modify them. Now we can see that the tail of the arrow is coming from the bond. We can see that the tail of the arrow is coming from the bond. That's a new situation that we haven't talked about yet, but I don't think it's going to be too surprising to you to hear that if the tail of the arrow is coming from the bond, that means that we're moving a pair of electrons out of that bond. We're moving electrons out of that bond. So, as usual, I think it will help to actually draw the pair of electrons that we're talking about. So we're moving this pair of electrons out of this bond. So I'm going to go ahead and erase that bond. That's what's indicated by the tail of the arrow. And now the head of this arrow is pointing directly at this atom. And I don't think it's too surprising that that indicates that we're going to be forming now a lone pair on this atom, a lone pair on the X, because the head is pointing to the atom. Again, in many cases in real life, we would not actually draw a lone pair that's formed. We would just indicate that by a charge. But for the time being, I think it actually will be a good idea to actually draw in that lone pair. So I'll draw that in. And again, as usual, I'm not going to worry about charges yet. So we'll leave the charges out. So since we're not worried about charges, these are our final products. These are the products that we would get in this case. So you can see again that the double-headed arrow tells you how a pair of electrons is moving. We took the pair of electrons out of the bond and instead moved them into being a pair of electrons on this X atom. And that means, so what type of transition have we made here? Well, we started with a bond. And we took the pair of electrons in the bond out of the bond and turned them into a lone pair. So this is a new third type of transition that we haven't talked about yet, taking the electrons out of a bond and moving them into a lone pair. That's our third transition. Let's think about this in terms of lacking, sharing, and owning to make sure that this is really legal. So how would we describe the pair of electrons in the starting materials for X and Y? Well, X was sharing the electrons in the bond, and Y was also sharing the electrons in the bond. And how about in the products? Well, now the pair of electrons has become a lone pair on the X, so now the X is owning that pair of electrons. And you can see that this Y atom here now has no connection at all to that pair of electrons. So now the Y atom is lacking that electrons. Lacking that pair of electrons. Remember that doesn't mean that Y completely lacks all electrons. I'm sure there's plenty of other electrons around the Y atom that we haven't shown. All we're trying to say here is that the Y atom lacks the pair of electrons that we're actually drawing, the pair of electrons that we're focusing on here. Is this legal? Well, yeah, sure, because the X atom is going from sharing to owning. That's just one step, sharing to owning. And Y is going from sharing to lacking. That's also one step, going from sharing to lacking. So those are both permissible steps. Try this example. I hope that every time I present an example, I hope that you're pausing the video and giving that a shot. We can start by redrawing the starting materials. Where are the electrons coming from? Well, the tail is on this bond, so the electrons are coming from the pair of electrons in that bond. So I'll go ahead and erase the bond. And where are the electrons going to? Well, the head of the arrow is on the Y. So in this case, we're forming a lone pair on the Y. I'm going to go ahead and draw in that new lone pair. And as usual, right now we're not worrying about the charges. Well, this is really very similar to that previous example, right? So this is another example of a bond to lone pair transition. pause the video and try this example. Let's start by redrawing our starting materials. Now, the tail of the arrow is again coming from a bond. So it again indicates that we're taking a pair of electrons out of a bond. So I'll go ahead and draw that pair of electrons in. And since the tail is on that bond, I should actually go ahead and erase the bond over here in the products. And where is that pair of electrons going to go to? Well, the head of the arrow is on the X, so that pair of electrons ends up on the X. So again, we had a transition of electrons from a bond to a lone pair. If you take a look at the three types of transitions that we've seen so far, you might have noticed something. Notice that for the first two transitions, I distinguished between forming a sigma bond and forming a pi bond, because the way you show that a sigma bond is being formed is different from the way you show that a pi bond is being formed. How do you show that a sigma bond is being formed? Well, to indicate a sigma bond, you put the head of the arrow pointing at the atom, pointing at one of the atoms that's going to have the new sigma bond. But how do you show a pi bond? You show that by having the head of the arrow pointing to the bond region between the two atoms that are going to have the bond. So this is something I didn't point out before. If you compare these two examples of forming a sigma bond and a pi bond, you put the head of the arrow in two different places for when you're forming a sigma bond or a pi bond. Again, to form a sigma bond, the head of the arrow goes directly on the atom. But for a pi bond, you put the head of the arrow between the two atoms in the bonding area. This is just the convention in organic chemistry. However, now over here, when we're talking about taking electrons out of a bond, I have not distinguished between whether we're taking them out of a sigma bond or a pi bond, because the notation is the same in both of those cases. We don't need to think about two separate cases for taking electrons out of a sigma bond or out of a pi bond. The notation is the same in both cases, as you can see by comparing these two examples. In the first example, we took the electrons out of a sigma bond, and we showed that by simply putting the tail of the arrow on the bond. Now, in the second example, we took the pair of electrons out of a pi bond, but we showed that exactly the same way by putting the tail of the arrow on the bond. So when you're moving electrons out of a bond, you don't need to distinguish between whether it's a sigma or a pi bond. The notation is the same either way. We've already seen, though, that when you're putting a pair of electrons into a bond, there is a different notation for forming a sigma bond than for a pi bond. Try this example. Where are the electrons coming from? Well, the tail of the arrow is coming from the bond. That means that we're moving electrons, the pair of electrons, out of that bond. So I'll draw in the pair of electrons that we're moving. And since the tail is on those electrons and we're moving those electrons, I'll go ahead and erase them on the product side. And the head of the arrow is pointing directly at the Y atom, so that pair of electrons is becoming a lone pair on the Y atom. One thing I didn't mention in the previous example, but that hopefully was clear to you, is that when the tail of an arrow is coming from a bond, you only erase one of the bonds. After all, here we started with 3 bonds, and since the tail is coming from one of those bonds, the product only has 2 bonds. But you never want to make more changes than are dictated by the electron-pushing arrows. So it would definitely be a big mistake to suddenly start erasing this either of these 2 bonds over here. We started with 3 bonds, and we are erasing one of them. You don't want to make any unnecessary changes. So each electron-pushing arrow only indicates the movement of 1 pair of electrons. Since this only indicates the movement of 1 pair of electrons, we should only be erasing 1 bond in this case. Once again, we've had an example here of a bond to lone pair transition. And again, we're seeing that it doesn't really matter whether you're taking the pair of electrons out of a sigma bond or a pi bond. Either from a sigma bond or from a pi bond, the notation is pretty much the same either way.